G'day viewers. In this segment I'll give you an overview of the routing topics that we're going to cover. Well, here's a reminder of where we are in the course. We've gone through some of the lower layers, the physical layer, the link layer. We're partway through the network layer. Don't worry, there's more fun to come. We previously talked about packet forwarding. Now we're going to get on to the business of routing. That's our topic for this unit. Before we dive into it, let me go over the distinction between routing and forwarding to make sure that you recall it from previous lectures. So forwarding is this process of when you get a packet, actually sending it on its way. So it's very much a local node process. You can see here a node gets a packet and forwards it, sends it in the right direction. And we've looked at that already and seen how IP forwards. Routing is the process of deciding which direction to send traffic when you get it. So that's an agreement process amongst all of the nodes to understand which way they should send traffic through the network. So if you like, if I was to draw the equivalent circle, routing is a process that involves all of the nodes in the network. So they're quite different in character, and we're going to look at routing now. Well, actually, the truth is we've already seen a very simple kind of routing called a spanning tree. We looked at a spanning tree when we looked at LAN switches, and the spanning tree provided basic connectivity in the network. So you can see here in the network of switches I have on the left, I've drawn a spanning tree. So some of the links are kind of turned on there, not all of them. So there are a couple of links in the network there that are unused. But this spanning tree is enough to connect all of the nodes. And in fact, it provides some path between every pair of nodes. For instance, between B and C, traffic is sent along this route. Well, that's great for being able to get something through it all, but it's not really a very good route in terms of using the network because you can see here that there is a link that's unused. So with routing, we would like to make good use of all of the links in the network because bandwidth is the key resource of the network, so we want to be able to use it well. What does that mean? Well, that's actually a little bit of a tricky subject that we'll look at in the next segment. But I'll tell you right now that we would expect good paths to be able to use all of the links in the network. For example, here we've shown links between B and E and C, I'm drawing over them, and B and C. These are all links in the network, and so we would like to be able to use all of them if we wanted to send traffic between those individual nodes. We couldn't do that with a spanning tree because the spanning tree can't have all of these links at the same time, or it would have a cycle and it would no longer be a spanning tree. So these kind of routes were precluded under our spanning tree. We're going to see how we can do better. And at the risk of going a little bit meta on you, I'd also like to provide some perspective on where routing fits in to the set of techniques we have in networking. Routing is really, you could think of it as one technique for allocating network bandwidth. The key resource of the network is the bandwidth it has to provide connectivity between the different points. We want to use it well, and the way we're going to use it is going to adapt along different timescales. The routing we're going to look at will find paths through the network which will adapt to equipment failures. So the routes will be recomputed if a link fails or if a node fails. Well, there are also other timescales on which we might allocate bandwidth. Starting at the longest timescale down here, there's provisioning. Provisioning is all about building your network to fit your customers and what they actually want to do with traffic. So it takes place at a long timescale, months, even years. An example might be if you had a lot of customers sending traffic between Seattle and San Francisco. It would be pretty sensible to build a network that had a direct path between Seattle and San Francisco in that case. If all traffic had to go via the east coast of the United States, that would be not so good. So provisioning will take care of that problem. And really, routing can only do what it can do on top of the network. It can't change where the links physically are. At a slightly slower scale than routing is traffic engineering. This is adapting the routing itself on a time scale of hours or so, minutes to hours to even days, depending on the overall load of the network. For instance, just talking about our United States network again, the load might be different at different times of day, and because of the time differences, you might have a lot going on the East Coast and the West Coast at different times of day. So you might want to specialize your routes for the busy hour on the West Coast and the busy hour on the East Coast slightly differently. Traffic engineering would let you do that, to adapt to the network load slowly over the day and the week. Routing, as I've said before, is about adapting to equipment failures, finding good paths around or using only the working equipment. So the routes are going to change on the order of minutes at most, we would hope, less often, unless we've got a lot of failures. There's also a much more dynamic form of bandwidth allocation that I'll call here load-sensitive routing. This is adaptation on the timescale of seconds around hotspots in the traffic. For instance, if there's a lot of traffic going between Seattle and that San Francisco, for some reason there might be a big pileup and a lot of congestion in Oregon. If that's the case, it might make sense to route some traffic via Chicago. That's going to be a longer path, but if there's really a problem in Oregon, like a traffic jam, it might be advantageous to take the longer route to get around it. So these are all important in the overall management of the network as different mechanisms to allocate our bandwidth, our key resource. The one we're going to focus on right now, and for all of this unit, is routing. So let's adapt to some of those failures. Okay, so for routing, it turns out routing is actually quite a large field in that there's a lot of literature on many different variants of routing. We're only going to focus on one kind of routing in our unit here. And I've shown here 4 different delivery models in terms of how the network can deliver traffic. We are going to spend all of our time looking at a unicast routing model. That's the one on the left here. Unicast is the kind of routing that takes traffic from a given source to a given destination. So you can see I've got a path through the network to send traffic between one source to one destination. Great, that's what you'd expect. So this is going to be our focus. I do want to point out to you that there are other kinds of delivery models, and they're important and useful in the internet. We don't have time to cover them in this introductory course, but if you're interested in some of these other models, I provided pointers to the sections. I'll just very briefly tell you what those models are. So in a broadcast model, you're trying to deliver traffic from a node to all other nodes of the network. So you can see here from the source here, if I follow the arrows, I'm drawing over it, it's maybe not the clearest to see, but hopefully you get the idea. If I follow these blue arrows, then I will end up delivering a copy of the packet to every other node on the network. That's broadcast. Multicast is like a subset of broadcast. In a multicast model, we deliver a packet from one node to a group of nodes, but not everyone else on the network. So you can see this tree here is a multicast tree that I'm drawing over right now, and it is delivering packets to these 2 pink nodes here. I'll just circle them, and not all of the other nodes in the network. So there's another 3 nodes there that aren't circled as end destinations that don't directly receive these packets. And a final other model is really a pretty interesting one if you would like to look something up. That's something called Anycast. The model here is that when you send to an Anycast address, the network will deliver it to the nearest member of a group. So you can see here, if we send from somewhere over here in the network, we might send a packet to this particular pink node here. That would be the nearest member of the group to these 2 sending nodes. On the other hand, if we send from a different destination to the same Anycast address, then we might be delivered to a different destination. It actually has the same address, and that is the closest instance of that group to where the sender was. This may seem like a very strange model, but it's actually quite useful in the network if you want to deliver packets, for instance, to the nearest root DNS server, or the nearest of one of many, a copy of many servers in a content distribution network. But as I say here, we're all going to focus on unicast delivery. Okay, now I just have a little bit more to tell you before we go ahead and look at some of these algorithms. I thought that I would give you some of the goals of the routing algorithms. This is really food for thought for you to keep in the back of your mind. We'll see different algorithms. How do you know which ones are any good? Well, these are the goals. This is what we want of our routing algorithms. First of all, we want them to be correct in finding paths that actually work to get from a source to a destination. That might seem obvious, but it'll turn out that it's a little harder than simply looking at a map and finding out which way to go for some of these routing algorithms, because they need to work in a distributed setting where everyone can't see the whole picture. We still want them to be correct in this setting. We want routing algorithms to find efficient paths that use the network bandwidth well. I haven't defined what well is yet, we'll get into that later. We also want these paths to be fair. Well, life's not entirely fair, so by fair I really mean that they shouldn't starve any of the nodes. For instance, it wouldn't be reasonable in our network to come up with good paths that work for most nodes, but we could only do it by making sure that some other node really didn't get to send traffic at all. That wouldn't be reasonable. Every node on the network should have the ability to send traffic through the network reasonably. And then here are another couple of important properties at the bottom. We would like fast or rapid convergence. So if we're adapting to failures, after there's a failure, we would like the routes to recover quickly because they need to do that before we can really use the network again. And a last goal is one of scalability. We know that many of the networks we build grow large very quickly. They become success disasters if you do it right. We would like routing schemes that can work well even as the network grows large. These are called scalable algorithms. Okay, and here is the setting for some of these routing algorithms. This is really what makes a routing algorithm interesting. Routing is really not like looking at a map and trying to work out which way to go, because the routing algorithm must operate in a decentralized and distributed setting. This is actually what makes routing both difficult and somewhat interesting intellectually. Now in this setting, just imagine there are all of these nodes in the network. They're all alike and they're all working on this problem of routing. No one's in charge, there's no controller. So somehow they're all going to have to work out how to agree on what to do. What's more, they can't all talk to one another directly. They can only talk to other nodes by exchanging messages with the neighbors that they're directly connected to. They don't yet have any other way to reach further away than their neighbor. They don't even know what the rest of the network looks like. They're all doing this concurrently, so they're all operating in parallel, which makes coordination even a little bit more difficult. And we also want them to be able to work and find correct paths even when some of the links and nodes may fail. Whichever links and nodes remain working, we would like all of that equipment to sort it out and simply find good routes. So you can see that it's really a pretty interesting problem. Well, we'll see some of the solutions to these problems as we go through the different topics. Last time we went through forwarding essentially. That was our IPv4 and IPv6 model, as well as other things like NATs. Now it's all about routing. So I'm going to tell you just about some different frameworks for routing, like what shortest paths are, as well as different algorithms for computing routes on some of these networks to find their way through. And we'll start by looking at enterprise networks or even individual ISP networks. And by the end of this unit, we will have grown in scope to consider routing across the internet where all of the ISPs and networks are combined together. You can look at this topic list if you like. That will just be your roadmap for where we're going to go through, but I won't go into it in detail now. Let's just jump ahead and see some of those units.